Okay, let's dive right into this. When most of us picture the Suez Canal, we probably imagine this calm, placid ditch out in the desert, right? Just a simple, quiet shortcut for global trade. But actually, scratch that. That is a deeply dangerous illusion. What we're really looking at in this explainer is a highly volatile, completely invisible physics trap. We're talking about a literal battleground of extreme hydrodynamics and relentless geotechnical warfare, where human engineering is going head-to-head with the raw, unforgiving forces of the Earth. Today, we're taking a heavily analytical look at the terrifying fluid dynamics governing this critical artery. Because out here, a single miscalculation doesn't just stop a ship, it literally paralyzes the entire world. And to truly understand the stakes here, you really just need to wrap your head around one massive number: 200,000. That's the tonnage of a modern megaship navigating the space. I mean, just imagine a steel skyscraper, lay it on its side, make it weigh 200,000 tons, and then move it through a channel so incredibly narrow you could practically skip a rock from the deck to the shore. At this immense scale, a ship doesn't just quietly float along. No way. It violently displaces a colossal volume of water, putting the vessel completely at the mercy of intense, high-stakes fluid dynamics. Literally every inch of forward movement is a tightrope walk, governed by physics that can turn deadly in a fraction of a second. And the foundational danger of this waterway? Well, it actually starts with its basic structural geography. Unlike the Panama Canal, which uses controlled locks, the Suez is fundamentally just a sea-level ditch. It relies on this natural buffer zone, called the Bitter Lakes, to absorb the shock between two massive bodies of water that are constantly fighting for dominance. And that leaves the entire rest of the channel completely exposed to these chaotic opposing forces. The parameters here are stark. Up at the northern end, we have the Mediterranean Sea, and down at the southern end, the Red Sea. Now, these two massive bodies of water possess entirely different tidal heights and tidal cycles. And because there are absolutely no physical barriers to stop them, a staggering volume of water violently rushes through this narrow channel every single day, just desperately trying to equalize. These currents don't just flow in one predictable direction either. They violently change direction twice a day. Now, I want you to apply those completely unpredictable cross-currents to a massive vessel stretching 400 meters long. These hidden underwater rivers, they are incredibly fast and totally unyielding. So when a 400-meter megaship hits one of these sudden cross-currents, the sheer force exerted on the immense surface area of that hull is staggering. The water can easily overpower the ship's rudder, overpower its engines, and violently push this massive steel leviathan completely off its intended course. Which brings us to one of the absolute most terrifying phenomena in maritime physics: hydrodynamic suction, or as it's analytically known, the bank effect. See, if a ship drifts even slightly too close to one of the canal's banks, the massive amount of water displaced by the hull suddenly has to squeeze through this incredibly tight gap between the ship and the shore. And if you remember Bernoulli's principle from physics class, as a fluid's speed increases, its pressure decreases. So that high-speed water trapped in the tight channel literally turns into a terrifying, invisible suction force. Boom. A low-pressure vacuum is instantly born right next to the hull. And this brilliantly illustrates the brutal split-second chain reaction that follows. Okay, so step 1, the ship drifts just a little too close to the bank. Step 2, that trapped water violently accelerates. 3, that deadly vacuum forms, instantly sucking the stern toward the bank while, get this, the immense pressure wave at the front repels the bow. So suddenly, the entire mass of ship pivots and violently wedges itself sideways right across the canal. This isn't just theory, by the way. This is the exact unyielding mathematical reality that caused the catastrophic Ever Given disaster back in 2021. Now, what's really interesting about this phenomenon is another wildly counterintuitive trap hiding just below the surface: the squat effect paradox. Because, you might logically think, hey, just push the throttle, increase your speed, and power through that tricky cross-current, right? But in a shallow, restricted channel, the exact opposite is true. As a massive ship moves faster, the huge volume of water underneath the hull is forced to accelerate just to get out of the way. Once again, Bernoulli's principle kicks in. The pressure drops beneath the vessel, and this terrifying physical paradox occurs. The entire 200,000-ton ship bodily sinks deeper into the water. Let that sink in. Increasing your speed literally forces your vessel to sink deeper into the earth. And you can probably see how this creates a deeply deadly psychological trap. Just imagine a captain feeling their ship getting pulled off course by the bank effect. Panic sets in. Human instinct absolutely screams at them to accelerate, to just power out of the slide and regain steering control. But by accelerating, they trigger the squat effect. The ship is sucked forcefully downward. If they squat too deep, that steel hull violently strikes the hard rock bottom of the canal. And the sheer kinetic energy of a 200,000-ton vessel grinding against bedrock, that will literally tear the hull wide open, instantly turning a simple steering error into a catastrophic shipwreck.
So those are the invisible hydrodynamic nightmares lurking down in the water. But what happens when the Sahara strikes back? Because the water is really only half of the battlefield here. The moment we step off the deck and look at the banks, we pivot from fluid dynamics to relentless geotechnical warfare. This is a war waged by millions of tons of shifting desert sand. The canal is essentially this massive open wound cut through one of the most volatile landscapes on the entire planet.
It is an absolute environmental onslaught from all sides. I mean, it's essentially the world's most high-stakes battle against a sandbox. From above, you have these relentless Sahara winds constantly blowing incredibly fine loose sand directly into the channel. And then from below, the violent kinetic wakes generated by those massive passing megaships are continually battering and eroding the structural integrity of the banks. So there is this constant, daily, existential threat of this vital global waterway simply filling up with dirt, choking the channel entirely, and trapping thousands of ships. To fight this, engineers are engaged in desperate, ceaseless human countermeasures. For starters, they operate a continuous 24/7 fleet of highly specialized vessels called suction hopper dredgers. These machines are just out there constantly vacuuming the encroaching desert right out of the canal floor. But they also have to actually armor the banks themselves. Along the underwater edges, engineers install what's known as riprap. These are massive, incredibly dense, interlocking armor stones. They basically form a brutalist underwater wall, physically locking the desert shield in place against the sheer, crushing weight of the Sahara. But even with all those dredgers and all that armor, the sheer volume of global traffic eventually pushed the canal to its absolute breaking point. And this is exactly what led to the mega expansion, otherwise known as the new Suez Canal. And let's be analytically clear here. We really shouldn't frame this as just some standard infrastructure upgrade. No, this was a panicked, multi-billion-dollar race against time to build a parallel channel. The objective was singular: prevent a total catastrophic gridlock that would literally trigger a global trade collapse. This scale of this operation was staggering. Engineers had to execute a hyper-accelerated excavation of 250 million cubic meters of soil, and they achieved this entire thing in less than 12 months, which is just wild. And this wasn't just digging a dry ditch either. Every single cubic meter was fought against immense, crushing, high groundwater pressure that constantly threatened to just flood and collapse the massive trench before it could ever even be stabilized. So the crucial point we need to take away here is that this expansion wasn't just about reducing a traffic jam. It was fundamentally about altering the physics of the environment itself. See, by opening a parallel channel and allowing for true two-way traffic, they drastically expanded the total water volume. The physics here are vital. When you push a megaship through a wider area, the massively displaced water actually has room to escape safely. So expanding the volume drastically drops the kinetic pressure beating against those canal walls. And that brilliantly mitigates both the deadly bank effect and the severe erosion of the desert banks. But as we look at the immense, continuous effort required just to keep this waterway open, we are really left staring at a deeply haunting reality. We are deploying multi-billion-dollar armor stones, massive 24/7 dredging fleets, and executing frantic terraforming operations just to maintain a very fragile equilibrium against relentless tides, vacuum suction physics, and shifting desert sands. It really forces us to ask one deeply unsettling question. Can human engineering permanently outrun the raw, uncompromising physics of the Earth? Or are we really just borrowing time before the desert and the ocean inevitably reclaim what is theirs? Definitely think about the invisible warfare happening in that ditch the next time you order a package from across the globe. Thanks for joining me on this explainer.